Hello, my name is Taiyan Hong, and this is my Lab 2 for Physics 2211. In this lab, we will observe the motion of an object falling relatively slowly and straight down from rest, analyzing the difference in motion affected only by gravity versus motion affected by both gravitational and drag force. We will be focusing on Newton's second law of motion by comparing experimental position and velocity analyzed through tracker and the predicted position and velocity generated by a computer model on GlowScript. To briefly preview the results, the experimental data from tracker and the computational models shared similar graphs. However, experimental data more closely resembled the model that incorporated drag force, indicating that there was a drag opposite to gravitational force that contributed to the net force on the system. The model with drag also modeled the terminal velocity of the object over time. Newton's second law draws a relationship between force and momentum. Net force is equivalent to the change in momentum over a change in time. This equation is significant because it relates physical observations of the system to its surroundings, which can then be used to predict the motion of the object in the future, shown by the velocity and position update formulas that we'll be using in the computational model. Gravitational force near the surface of the Earth is equivalent to the object's mass times g, the acceleration due to gravity on Earth, in the downward or negative y direction, hence the negative sign. Using the formula for gravitational force, force of gravity is equal to the universal gravitational constant times the mass of the two objects divided by the squared distance between the two objects. We can find that g is roughly equal to 9.8 meters per second squared. Because of the air in the surroundings, there is also a drag force exerted on the system opposite of the direction of the force of gravity. In this lab, we will declare it down to be the negative direction. The formula for the drag force is the product of the proportionality constant and times the square of the magnitude of the object's velocity, which is a scalar. Over time, drag force increases as the magnitude of the velocity increases due to gravity. The system is the eraser and the surrounding is everything else, like the Earth and the air. The net force in Model 1, without drag, is equal to the force of gravity, whereas in Model 2, the net force has two components, the force of gravity and the drag force. For the lab, we will first record the motion of an eraser falling vertically from rest at a rate somewhat slower than the falling rock. Then we will import the video into tracker and track the eraser's position from frame to frame, then use the data to produce a position with its time graph. We will also generate two computational models of the eraser's motion over time using the GlowScript starter code, one accounting for drag force and the other not, and graph the eraser's expected position and velocity over time. Finally, we'll compare the tracker data to the computational models and analyze the results. Here is the video of the falling eraser. Initially, we assume the eraser to be at rest, therefore initial velocity is 0. The eraser has a mass of 0.029 kilograms and a length of 0.004 meters. Initial t is 0 and the change in time is 0.401 seconds. The length of the video was 0.401 seconds and 12 frames, therefore the frame rate was roughly 29.9 frames per second. The origin was set to the initial position of the eraser as shown above, with the downward direction being negative. In order to create a model simulating the eraser's motion, I had to update the GlowScript starter code. I added the mass, initial position, delta t, the start and end time of the motion, and the magnitude of the acceleration due to gravity near Earth's surface, g, which we found earlier to be 9.8 meters per second squared. I also added the velocity and position update formulas in the while loop so that with each iteration until t equals 0.401 seconds, the changes in velocity and position would be reflected in the model. In the first model that only accounted for the force of gravity, the drag force constant was 0, therefore F0 was set equal to only the weight force. In the second, the drag force constant was set to a positive non-negative number 0.0017, which we found by approximating the model data to the experimental data calculated through tracker. We find the drag force using the formula for drag force using the constant and the object's velocity, then we set net force as being equal to the sum of the drag force and the weight force. Here are the graphs generated by the two models. When we graph the three results together, where position is measured in meters and time in seconds, we see how the lines almost overlap initially but begin to diverge over time. The blue represents the experimental data, the red represents the model without drag force, and the green represents the model with drag. The model with drag more closely resembles the experimental data over time. Model 1 without drag force overestimates the change in position because it does not account for the drag force working opposite to the gravitational force. This reduces the net force and the acceleration of the system, therefore reducing the change in velocity and position over time. This suggests that there was a drag force acting on the falling eraser during the experiment. Slight variations may be due to error in tracking the position of the ball, possible distortions of the video in motion and other axes, and rounding errors. What does this mean? Which models predict the terminal velocity? The second model that incorporated both the force of gravity and the drag force for the net force predicts the terminal velocity. Comparing the velocity versus time graphs, we see that the model without drag shows a linearly decreasing velocity, whereas the model with drag force shows that the change in velocity decreases over time, eventually reaching an asymptote that is the terminal velocity. What if? Would the terminal velocity be the same if the ball was thrown downwards? When the initial velocity in the model with drag is changed to a non-zero constant, the graph reaches the same asymptote across a shorter change in time. Therefore, we can conclude that the terminal velocity remains constant regardless of the initial velocity. To conclude, Objects falling from rest experience gravitational force and a drag force that is in the opposite direction of the motion and is directly proportional to the object's velocity. Due to drag, objects will eventually reach terminal velocity when the magnitude of the drag force is equivalent to the magnitude of the gravitational force.